that all went well. Thanks so much for having me. It's been a while since I've given a seminar. Being an acting dean takes away time from the lab that I'd rather be spending in the lab, but sometimes those administrative duties call. I appreciate this seminar series in particular because it gives me a chance to talk a little bit less about the science and maybe some about the path that I took to get to where I am. Especially for young investigators, I think it's important to hear that the path isn't always a straight line. I just had a conversation with a high school student last week, and she was dead set on going to medical school, and she's a sophomore in high school. And I said, listen, that may be where you end up, but there's a lot of zigs and zags that might happen along the way that derail you a little bit, and that's okay, because it's during those zigs and zags that you learn. And so I'm going to talk a little bit about my path because there have been a lot of zigs and zags along the way. Before I do that, I like to start at the end. Most people acknowledge at the end of their talks. I like to start at the beginning because the work that I do in the lab wouldn't be possible without the wonderful team that I've assembled in Indianapolis. This is the current group. This is also a shameless plug that I'm actively hiring at all levels. If you're interested in what you hear today and then you are looking for your next opportunity, please reach out to me directly. Be glad to talk about things. I'm not going to go into the details of the funding itself, but we are funded across multiple NIH institutes, NSF, and the VA right now. So as Mohammed was indicating, we've got a rather broad portfolio of the work that we're performing. And I'll touch briefly on some of this at the end today, probably the last half. We'll see how much time we have, but I want to start at the beginning. And the beginning for me was Shelby County, Indiana, which for those of you who know anything about Indiana, there are a lot of cornfields. And this little circle down here is outside of Indianapolis, and this is where I grew up from the time I was 5. This is an overview of what that area looks like today. When I was younger, none of these houses existed. This was all cornfields, and my house is sitting right here. I was the youngest of 3 boys, and my mom was a single mom living in Indiana, and my brothers and I ended up being first-generation college students. So growing up, we didn't really have resources. We didn't have anybody to talk to about what it might look like to go to college because there's nobody around to really tell us that. What I did a lot when I was a kid is stared up at the stars and wondered, what it was going to be like to get out of the cornfield at some point. And this really grew into a desire to become an astronaut. Now, if you can see me on the screen, I've got glasses, I've got really terrible eyes, and it was unlikely that I was going to follow the normal path to becoming an astronaut, which is really to go into the military and to become a pilot. So I got this harebrained idea that becoming a scientist was probably the way to go. And I spent, time in grade school and high school not knowing what kind of science I wanted to do, but really trying to bolster myself in math and science classes as much as I possibly could to get prepared. And at some point along the way, I learned about aerospace engineering. I couldn't have told you what it was because I didn't know what an engineer was, but it sounded like a good idea because it had space in the name. And so when many of my friends headed north to Purdue to study engineering, which is about 65 miles north of Indianapolis, I decided I wanted to go someplace where I knew nobody and could start a life just, completely new. And so I headed south to Atlanta, where Georgia Tech is. They have a highly rated aerospace engineering program, and I thought this is where I'm going to start on my path to go forward. And so Atlanta is a much larger city than Indianapolis, and I wouldn't be living in cornfields anymore. I think Indy has a population of about 1 million people, and Atlanta is currently around 6 million, so it's quite a bit larger. And Georgia Tech is smack dab in the middle of Atlanta. I spent a lot of time when I was at Georgia Tech staring up at Tech Tower. This was right outside of the aerospace engineering building. But I'm also a huge sports fan, and I spend a lot of time at football games as well. And so this is Georgia Tech's stadium, and this little green box down here shows the seats that somehow, as a freshman, we were able to get sitting right around the 20-yard line. These are really good football seats. They're so good, in fact, that my friends who still live in Atlanta currently have those exact seats as adults, 20-year alumni. So I don't know how we got those seats while we were there, but we managed to get them, and it was a great experience. Georgia Tech prides itself in a co-oping program, and most students co-op while they're there. And what that means is that you work one semester, and then the next semester you're in classes, and you alternate back and forth throughout your college career. And it usually extends the college career to about 5 years, which is what it did for me. And so I started while I was there working at Delta Airlines, which, for those of you who don't know, their world headquarters and is in southern Atlanta. This is an overview of the Atlanta airport here, which is one of the busiest airports in the world. And then this box in red is at Delta's Technical Operations Center. It's where they do all of their major aircraft retrofitting and maintenance. And if I Zoom in a little bit closer, you can see here in red, this is where all of the engineers live, in a room on top of this much larger facility, which is the shop floor where various aspects of the aircraft are, retrofit and repaired. I mean, you can see over here, there's a tarmac and these hangars, there's planes all over the place. So for a person who was actually interested in aerospace, it was very exciting. I worked in propulsion engineering, and I worked on this particular engine, which is the JT8D engine, which at the time was a part of the 727, 737, and MD-88 fleet of Delta. This is the largest portion of their fleet. And if you can imagine, I started there as a freshman aerospace engineer writing repair orders on engines of some of their most major aircraft, which is kind of a scary thought. Now, granted, I was overseen by other engineers, but the fact that I was doing anything that went onto a plane is a bit scary looking back on it now. So lots of aspects of the job were exciting, but for most of the time I was there, I felt like this. And if those of you who don't know this is Milton. He's a character from a movie called Office Space, and what you can see is he's sitting inside of a cubicle lit by fluorescent lighting. And I won't exaggerate when I point out that this red block that I highlighted here was a room of 300 cubicles, just like Milton's, with no windows at all, mostly filled with older white guys that had worked there for 30, 40 years. And I became terrified that this was what my life was going to be. And I didn't know what to do. So I knew I didn't want to be stuck in a cube. And much of my life, in addition to wanting to be an astronaut, I also really liked medicine, but I didn't want to be a medical doctor. I was also pretty far along in my aerospace undergraduate degree, at that point, 3 years in, and it was a bit too late to switch in an efficient way. Georgia Tech had just started a biomedical engineering program. At the time, there weren't very many in the country. Now there's many, I think close to 200 accredited programs, but back then it was a little bit rarer. And having just started, I was given permission to take some graduate level classes in BME. And the very first class I took was a cardiovascular biomechanics course. And I did worse in that class than really any other class I took as an undergrad, and it probably should have scared me away from biomedical engineering. I was sorely unprepared from the biological side. I was sorely unprepared from the mathematics side, and I really should have been pushed away, but I wasn't. And I continued forward and ended up taking my next class, which was called Systems Pathophysiology. And it was in this class that I first learned about bone. And I remember, if any of you know the name Bob Goldberg, he was a faculty member at Georgia Tech at the time, and he taught the section on bone, and it totally hooked me. Bone structural, right? And for me, the part of aerospace engineering that I liked the most was structures. I really liked the design of wings. I love this picture because, for those who don't know, before commercial airliners are deemed airworthy, they go through a large series of tests. And this particular test always fascinated me because they take the wings, and you can see how high these wings are flexed up. They bend these wings all the way up until they fracture. And they've got sensors all over the wings to measure how much deflection and force the wing is undergoing. But the point is, as an engineer, you need to design things that are strong enough to do their job, but not so strong that they're over-engineered. Because if they break before they're supposed to, people fall out of the sky. But if they break too late, then you've over-engineered and put a lot of cost into the structure that you're building for a profit. And so I really liked aircraft structures, and all of the engineering principles that I had learned in aerospace engineering were 100% compatible with studying something like bone. But as opposed to this static structure that you find in an aircraft, bone's really awesome, right? It's alive and it's metabolic, it's highly active, it's adaptable, and it's self-healing. And this self-healing aspect was really cool to me because a lot of what I did when I was working in the airline industry is fix damaged parts. And to find out that there's this biological mechanism in bone to repair itself was just, as a 22-year-old kid, I was totally hooked. So I took a leap of faith and decided to enter into a biomedical engineering graduate program. Now, coming from aerospace, I had no biological background. I had no lab experience. In fact, I had never even stepped into a wet lab. And I'm convinced that if I made this switch today, I wouldn't have been nearly as successful as I was at the time. But I took a risk, and someone took a risk on me, and I entered the PhD program of biomedical engineering at Michigan in 2002. So this is North Campus of the University of Michigan. If I go back, Michigan's split into two main campuses, the Central Campus and North Campus. All the engineers are stuck up on North Campus. And although my classes were up here, I was actually lucky enough to be in the dental school at Michigan. So I got to live on Central Campus, which was great. Spent a lot of time watching football games at Michigan too, as opposed to my seats at Georgia Tech. My first, second, and third year at Michigan, I had seats in row 79 at Michigan Stadium. And again, to put that into perspective, this is where I was at Georgia Tech. So I spent 5 years there as a PhD student and then continued on in the Department of Chemistry as a postdoc until 2010. And at that point, I made the trek southward to Indianapolis, where I've been ever since. So this is IUPUI's campus in Indianapolis. IUPUI is Indiana University, Purdue University in Indianapolis. I've been here as a director of my lab since 2010. I traversed through the academic ranks and took over as the department chair in 2020, just as COVID was getting ready to hit. I've had the fortune of being the acting dean of the School of Engineering and Technology since July of 2023. And in July of 2024, this campus is getting ready to fracture, and my department will become a part of Purdue University, and the rest of campus more or less will stay with IU. And none of that really matters for today's talk, aside to say that I'm not physically going anywhere. Right now, this is where my lab and my office are. And what's great from a biomedical engineering perspective is that I'm on campus with a very rich biomedical ecosystem. Within a half-mile radius of my lab and office, there's the main IU hospital, the Simon Cancer Center, the Riley Children's Hospital, Eskenazi Hospital, and the VA Hospital. So we're talking about 5 major hospital systems right here within spitting distance of our lab. So from an educational perspective, this gives our students in Indianapolis a very strong and unique opportunity to directly interface with the medical environment, which will continue after the Purdue split. Speaking of the Purdue split, it's going to start with these 5 buildings, and in addition, this 28 acres just north of where our buildings are. So Purdue University will be building a university system right in the heart of Indianapolis. And for me, this is great because I get to be an engineer and still interface with those collaborators and colleagues that work in the School of Medicine, which is just across the street. While I've been in Indianapolis, I've also built my family. I think it's really important to point out how, for me at least, my mental health is tied to my work-life balance. And you'll hear that term a lot. It means different things to different people. For me, it really means having an outlet that's outside of the work that I do in the office and in the laboratory. Without this, I think I'd go crazy. And so these are my 2 boys. My oldest here, Oscar, just turned 14 years old last Friday, which is crazy to me. He was born just before I moved to Indianapolis. And so it kind of tells how long I've been here. And then my youngest, Archie, my wife, and then our COVID dog that we picked up in July of 2020. And it's just as much a part of the family as everyone else. So I kind of blasted through that, but I think it sets the tone for kind of how I arrived where I am. And now I can talk a little bit about what we do in the lab. So my lab's name is the Bone Biology and Mechanics Lab. And as its name implies, we study bone mechanics, which is the ability of the skeleton or bone to effectively bear loads, and mechanobiology, which is the cellular response to those mechanical stimuli. And for everything we do, and this really goes back to what Mohammed was saying in the beginning, my research portfolio is fairly broad, but it all comes back to the same kind of major principles. And that is that we study bone as a hierarchical material, recognizing that this means that it has structures at one length scale that are composed of elements which themselves have structure at smaller length scales. This is a lot of words. It doesn't necessarily mean much until you kind of see it in action. But as an engineer, the reason that we design structures in a hierarchical manner is that it allows us to use less material to achieve some desired mechanical performance. And going back to this less material part, right, that's as I said before, if you build a structure that has more material than it needs, you're over-engineering and costing money. And that's not what you want to do when you're trying to make profit. Well, the body actually uses this hierarchical principle for a similar reason. Bone material is dense. It's much denser than other tissues in the body, and it's metabolically expensive to carry around extra material that you don't need. So bone has been not developed. It's designed itself over time and evolved to be able to perform mechanically in a way that doesn't require all of the extra material it might otherwise need. I'm not going to go through the hierarchical structure of bone because I think you're all aware of it. I'm just going to blast it up here really quickly to say that once we get below the organ and tissue level and we talk about trabecular and cortical bone, from this kind of nanoscale below, bone is bone, and it's all composed of mineralized collagen fibrils. And mineralized collagen fibrils are a 2-phase composite that's a relatively soft and ductile organic phase, or collagen, that's impregnated with and eventually surrounded by a much stiffer and stronger reinforcing mineral phase. And then what's coming to I know the front of research these days is the understanding that there's interfacial water that exists between the collagen and mineral that's critically important to the mechanical performance. In some ways, that allows for efficient transfer of loading from one to the other. It also allows for sliding to occur between the mineral crystals and the collagen, which is critical to the overall way that bone behaves as a whole. And I'm not going to go too much into the mechanics of bone, but keeping in mind that collagen, mineral, and water are critical, we use a variety of techniques across that hierarchical structure to characterize various aspects of bone. So my heart and soul are in mechanics. And so I start with the mechanics slide because that's what everything comes back to. Every study we do has some form of mechanical endpoint in it. Most often it's whole bone mechanical testing, which you can see here on the left, but we also do a variety of fatigue and fracture toughness testing, where fatigue allows us to outside of the body's repair system, to characterize how a bone holds up to cyclic damage over time. Fracture toughness can give us a viewpoint into the material's ability to resist the propagation of a crack that we place into the structure. And then it would be remiss of me to not mention some of the smaller scale things that we do, because that's really where my independent career started, utilizing atomic force microscopy. This is a beautiful image from Chelsea Heveren's lab showing a single osteocyte and a map of elastic modulus around that osteocyte, which was acquired using atomic force microscopy. So all the way from the smallest scale structures up to a whole bone level, we can use mechanical testing methods to characterize various aspects of the mechanical performance of the skeleton and of bone. We do a lot of imaging. I think that that's important to this group, right? So our bread and butter is micro CT. We use it every single bone that's used for any of those mechanical tests I showed on the previous slide. We'll go through a CT test or a characterization first. It gives us information about the microstructure, but it also allows us to do various types of mechanical normalizations, which I'll get to a little bit later. SEM, polarized light microscopy, AFM, all of these things give us different windows into the structure of bone and bone tissue. We also look at tissue composition and turnover. So again, dynamic histomorphometry is no stranger to anyone here. We use Raman spectroscopy and FTIR to characterize direct chemical composition measures, primarily of the collagen and mineral components of bone. And then more recently, we've gotten into using NMR to characterize tissue hydration. And so a lot of the interventions that we use are focused on that interfacial water that exists between collagen and mineral. And so this gives us insight into how those treatments may be impacting the water phase of bone. So I like this slide because it's designed for non-engineers to make things simple. We're interested in preventing fracture in bone. And so I choose just one mechanical property, in this case, strength. And it's intuitive to think that if the loads the bone encounters during daily activities exceeds its strength, you're going to get a fracture. What's less intuitive is what leads to bone strength. A couple of features are pretty easy to just view from the outside. Bone mass and geometry. So more bone and bone that's organized better in three-dimensional space will intuitively have higher strength. And this is important because clinically speaking, the most common way to kind of characterize bone fracture resistance is a DEXA scan. And this is actually a DEXA scan of me that was taken at the School of Medicine's FitCore. This is my whole body DEXA, my proximal femur, and my T-score, which thankfully is in the green, showing that my risk of fracture at this young age is fairly low. But the problem is that DEXA only characterizes the mineral content of bone, the quantity and its organization. And usually more bone is better. But it turns out that there's something missing from this. I love this graph because it hammers home exactly what I mean. On the x-axis here is bone mass, and on the y-axis is fracture risk. And these various lines are just various aged people. And what you can see is that any bone mass, if I just choose some arbitrary bone mass and I move up in the y direction, there's an increase in fracture risk with age that's clearly not being captured by this measure of bone mass, suggesting or arguing that something beyond mineral and mass are important to fracture resistance. And the kind of nebulous global term that's used to describe what this other thing might be is tissue quality. And this is really where my lab focuses, is trying to understand the impacts that tissue quality have on bone fracture and fracture resistance. So when we come back to this picture of mass and geometry, there's this whole big thing of material level properties of the collagen, mineral, hydration, damage. There's other things that can be lumped in here. I just chose those four to kind of set the tone here. What's complicated about bone is that it's not static and inert, right? It's adaptable to a variety of biological and mechanical stimuli. And so to really understand and study bone mechanics and fracture resistance, we have to view this entire thing as a whole. And to really understand what's driving fracture, we need to consider all of these other things. And that's exactly what we do in my lab. Under a variety of different disease states, we try to understand how fracture is impacted. Some of these disease states are direct insults on bone itself. And I'll talk about osteogenesis imperfecta in just a second. Others have less direct impacts on bone. And in some ways, when I start to talk about the disease I study, people are like, what do you mean that has an impact on the skeleton? And so I guess part of my job today is to convince you all that some of these diseases are just as important as those that are primarily impacting bone. And then we use a variety of anabolic and other pharmaceutical interventions to try to really modify tissue properties. And my specific interest is in collagen and water, but obviously mineral is important as well. So I don't want to downplay the role that mineral plays in bone. But our overall goal is to increase quantity and quality in complex disease states. And I'm going to get through a portion of today's talk where I talk about one specific complex disease state as an example, not as the only disease state of interest. But I like to start with what I think is a less complex disease state, and that is osteogenesis imperfecta, because it really sets the tone for how a single, very small change in collagen can detrimentally devastate bone. So I'm sure you're all aware, osteogenesis imperfecta is known as brittle bone disease. We'll come back to that in just a moment. It's a heritable disorder that's characterized by one of probably 2,000 different possible alterations that can occur in type 1 collagen or in collagen-related proteins and enzymes. And because of the variety of different mutations that can drive the disease, there's a wide spectrum of clinical severities. Everything from spontaneous fracture following very minimal trauma to perinatal death due to crushing injuries during birth. For many, it's an unknown disease because it doesn't impact very many people, maybe 25 to 50,000 Americans. This is probably an underestimate of the number that have the disease, just given the number of various clinical manifestations of the disease itself. I always like to have a pop culture reference, and for many years I used this one, realizing that now it's dating me because this movie came out in 24 years ago. But the movie's Unbreakable. Bruce Willis was a superhero fighting against Samuel L. Jackson, who was a supervillain. And Samuel L. Jackson is a wheelchair-bound man called Mr. Glass, and he has osteogenesis imperfecta, and through his entire childhood and adult life, he suffered from fractures that have caused malformations of many of his bones. So this was in 2000, and back in 2019, so a little bit more recent, was the sequel to the movie. So I can use a relatively new pop culture reference to keep my seminars, I guess, a bit light and up to date. So to understand what's happening in OI, or really any disease that's going to impact collagen, we have to talk a little bit about collagen synthesis. So collagen is initially synthesized as a polypeptide chain of amino acids that has, for most of the molecule, a repeating triplet motif of glyXY, where gly is glycine, and I'm going to come back to how important glycine is in just a moment, and X and Y are most often proline and hydroxyproline. Because of the specific amino acid sequence, this chain takes on a left-handed helical conformation, and then 3 of these left-handed helices counterwind into a right-handed triple helix. So mechanically speaking, we've just developed a very, very strong molecule. It's incredibly strong in tension because of that winding and counterwinding that I just described. It takes on this tightly packed triple helical structure, and it's critical that glycine is every 3rd amino acid, because all of the side chains of those glycines, these hydrogen atoms, tuck themselves down the center of that triple helix. And any other molecule, any other amino acid that's substituted in for any of those glycines wouldn't be small enough to fit down the middle of the helix. And this is exactly what happens in osteogenesis imperfecta, where the majority of those thousands of clinical types of cases are driven by a glycine substitution. So we've got these non-helical ends on collagen. These pro-collagen ends are cleaved off, leaving behind a mature tropocollagen molecule, which then self-assembles into a parallel staggered array. I'm sure many of you have seen this Hodge-Petriska model of collagen, where there's gaps and overlaps that exist within the structure, which drive the characteristic feature of a collagen fibril known as the axial deperiodicity. And if you ever see an SEM or an AFM image of collagen, you will always see this deperiodicity. Within that triple helical, or sorry, within that that parallel staggered array, we get a variety of enzymatic crosslinks that form. And it's important to note that these are enzymatic, meaning that they're tightly regulated. They can only occur in very specific locations within the collagen and only in a very specific amount. And this type of cross-linking gives stability to the collagen structure. So these are considered good. We're going to come back to why that's important in just a moment. So back to OI. Most OI cases are driven by point mutations in collagen. A substitution of a triple helical glycine drives many of the cases, or splice site mutations of the collagen molecules themselves, alpha 1 or alpha 2 chains, or the accessory proteins that are necessary for the formation of the structure. In the less severe forms of the case, we just get an underproduction of normal collagen, but in the more severe forms, in the forms that I study, you get delayed folding, overmodification, and oftentimes incorporation of mutant alpha chains into the collagen scaffold. So when I started my career, the reason that this disease state was so attractive to me is, as an engineer, it gave me a lot of control. I could look at a change in the very lowest level of this hierarchical structure, and then I can study the impacts that that single change, that known change, had at all levels above it. And so for the first 10 years of my independent career, I almost exclusively studied OI, simply to get a feeling for how we were manipulating all of these various aspects of the disease state. I'm going to very briefly talk about some results from this one study in OI. This one in particular used the OIM mouse model, which is a single nucleotide deletion in the alpha 2 chain, and it leads to a non-functioning alpha 2 chain. We're working with heterozygous animals in this case. And what that means is they don't have the ability to form normal alpha 2 chains at all. So all of their collagen ends up being alpha 1 homotrimers. And it leads to a fairly severe form of OI where there's all sorts of spontaneous fractures that occur in these animals. And we did a lot of different things with this particular study, but I'm just going to focus on two properties in particular: micro-CT and whole bone mechanics. To kind of talk about mechanics, I don't want to give a primer on the theory of bone mechanics. That's not my goal here. But I will say that many of you have probably seen a force displacement curve that looks like this. This is the type of curve that's generated when we mechanically test intention, compression, or bending, and it tells us a lot of information. This particular curve is specific to the whole structure, which means that within this curve, we are focused on not just material properties, but also the size and shape of a bone. And as an example, if I take two pieces of wood that are made of exactly the same material, it's intuitive that the larger piece of wood is going to have stronger properties and stiffer properties, right? So it doesn't really tell us anything about the tissue itself, which is where a lot of my interest lies. So we can use engineering principles to normalize away those contributions from the size and shape to generate an analogous curve, the stress strain curve, that now is an estimate of what's happening at the tissue level. And we do that in really all of the studies that we perform, using micro CT as the way that we normalize away that size and shape characteristic. So in this particular case, this is a curve that may have been generated from a real test. These are theoretical curves. I use them to teach. This is what it really looks like. I want to point out, I kind of, in my mind, when I look at these curves, break things into two regions: the pre-yield region and the post-yield region. Yield, as defined here on this curve, is the area on the curve where behavior begins to become nonlinear. And it's important because everything that happened on this curve prior to that yield point is more or less reversible, meaning that when I load and unload within this region, I'm technically not generating any damage within the structure. And if I were to unload completely, I'm going to end up back at this 0, 0 point. So when I think about what's happening in the pre-yield region, I really think about properties associated with stiffness and strength, or the ability of the structure to resist deformation, and ultimately the onset of damage. Because since I'm not passing the yield point, I'm not generating damage in the structure. Being stiff and strong is good. An aircraft wing, we want it to be stiff and strong. We don't want it to develop damage, because if it does, we have to take it off the wing and fix that damage, or it's going to lead to a catastrophic failure. In a biological system like bone, where damage is repairable, it's actually beneficial to have what we call a large post-yield region, because this region is characteristic of ductility and toughness, or the ability to tolerate the presence of damage. So the hallmark of a brittle behavior like OI bone is a lack of this post-yield region. And what that means is, like a piece of chalk, it may be pretty stiff, but as soon as damage develops, the sample fractures. Well, this is no good in the body. What we need is a bone that's capable of tolerating damage presence because we have the biological mechanism to go in and fix that damage. So in OI, in this particular model of OI, you can see these are schematic representations of cross sections of the femur. And it doesn't take a bone person to recognize that the OI bones are much smaller than their wild type counterparts. And as expected, this leads to structural level properties that are deficient in terms of mechanics. As you would expect, a smaller bone should have lesser properties. But when we normalize away those differences in geometry, it turns out that the tissue level properties are also deficient. And so this is a disease state where inferior tissue properties lead to weak and brittle tissue. And then in cases like this, where there's deficiencies in both the quantity and the quality of the bone that's present, if we were to just use an anabolic treatment to try to increase bone mass, it might not be enough to overcome the material property deficiencies, in this case, mostly of the organic phase, which drives other deficiencies in mineral and hydration. And so this leads us to take a step back and to ask the question that in a complex disease state like OI or some of the other diseases that we're studying, where we've got deficiencies in both mass and quality that are driving multi-scale mechanical deficiencies, what is it that we need to do to come in and combat those deficiencies? And the approach we take is to combine anabolic therapies that improve mass with other pharmaceutical interventions that have the ability to improve matrix quality, to ultimately improve skeletal outcomes, increase mechanical properties, and reduce fracture risk. And so I could stop right here, and I probably will in just a moment, to open things up for questions, because this framework is what we use to study many diseases in my lab these days. It was about 8 years ago that, out of luck, I got wrapped into a study involving chronic kidney disease. And again, I say, what does kidney disease have to do with bone? Well, it has a lot to do with bone. But I happened to be in the right place at the right time and started studying kidney disease. A few years later, due to a review on an NIH R01, a reviewer said, you really should be looking at the impacts that diabetes has on collagen. And I said, you know what? I really should be looking at the impacts that diabetes has on collagen. And fast forward to 2024, and most of my lab is now focused on diabetes, chronic kidney disease, and their interaction. And so I'm going to briefly talk about it for just a second to set things up, and then I'll stop and open things up for questions. So,
Okay.
oh, go ahead.
Yeah, you wanna let people ask questions, or you
Sure,
you just
sure. We can stop now. I'm fine with that.
Wonderful presentation so far. We really enjoyed. Congratulations. So any questions so far? Okay, I think we can go ahead.
Feel free to interrupt me. I'm a very informal person, so okay. So as I mentioned before, osteogenesis imperfecta, right? It impacts maybe 25 to 50,000 Americans. It's a fairly rare disease. Diabetes is not a fairly rare disease. It's estimated that 11% of Americans, and this number is a little flexible, maybe 37 million people have diabetes in the United States. And this is nearly twice the global average. I love this picture on the right because it shows all of the various body systems that suffer from the impacts of diabetes. But what it doesn't show is anything about bone, which I think is an oversight. So I use this to highlight how short-sighted the picture actually is, because bone is actually very impacted by diabetes. I am not a biologist and I am not a signaling expert. And so sometimes when I see pictures like this, I get a little anxious. But my point here is that there's a lot of things that are impacted by diabetes in the skeleton. My focus has primarily been on the development of advanced glycation end products, or AGEs, in bone. And I'll come back to this picture in just a second. So many of you have heard AGEs, I'm sure. And I think many of you have actually seen it and maybe not known it, because AGEs form when you take proteins and sugars and expose them to heat. And it's a form of the Maillard reaction, which for any cooks or anybody who's ever toasted a piece of bread, you've actually seen this firsthand. When you take a piece of bread and stick it in a toaster, or you put meat or tofu on a grill, and that browning develops in the tissue or in the food, that is the Maillard reaction, and it's the same type of reaction that underlies the formation of AGEs. Here it's happening in food. Here it's happening in collagen. When you expose collagen, which is protein, to a high glucose environment that exists in diabetes, you get the development of cross-linking. Now, I already mentioned enzymatic cross-linking, which is a good thing. Occurs at very specific locations in collagen, tightly regulated by enzymes. Non-enzymatic crosslinks are not. They are indiscriminately formed anywhere that there's exposed protein, sugar, and warmth. And it turns out that they can form in excessive amounts within collagen, and these may have detrimental impacts on the skeleton. And I'm saying may have because for the past 3 or 4 years, there's been some contentious debate in the literature as to whether this formation of non-enzymatic crosslinks in collagen are ultimately responsible for the fragility that exists in diabetic patients. So I'm just going to take it as if they do, because we're going to move forward with that. But in addition to the presence of the AGEs within collagen, their presence also activates receptors for AGEs. And the downstream effect of this is an increase in chronic inflammation that, among other things, can drive bone resorption and lead to porosities within the cortical bone structure, which we'll come back to in just a moment. Now, 10% of Americans, in my previous slide, it said 11%, but we'll go with somewhere in there. 10 to 11% have diabetes. 30% of these patients will develop chronic kidney disease. On its own, CKD impacts about 1 in 7 Americans. And it turns out that diabetes is responsible for approximately 45% of those chronic kidney disease cases. And so these two diseases go together very, very well, but they each independently have their own detrimental impacts on the skeleton. Now, the way that diabetic nephropathy, or the development of kidney disease and diabetes, works is that within the glomerular capillaries, which is the primary filtration unit of the body, diabetes drives chronic increases in blood pressure and inflammation. In addition, AGEs, which form in bone, also form in these capillaries. And the combination of these over time leads to the breakdown of the capillary walls and ultimately to one of the clinical hallmarks of diabetic nephropathy, which is a progressive increase in protein excretion in the urine. This is a picture of two glomeruli, the healthy one on the left and the diabetic nephropathy one on the right. And you can see a complete loss in the cellular structure on the outside of this. It's a really debilitating disease on its own. Now, some chronic kidney disease cases progress into what's known as mineral and bone disorder. And this is really a triad of bone abnormalities, vascular calcifications, and laboratory abnormalities that lead to cardiovascular disease, fracture increase, and mortality. And this graph really shows all of it. This is a graph showing various stages of CKD moving from black to blue. And what I want you to appreciate is that regardless of the stage of CKD, including CKD stage 3, which is largely undiagnosed at that point, there's a marked increase in fracture risk in patients suffering from the disease. 50 to 60% of those patients will die within 1 year following the fracture. So it's a really the skeletal impacts of just CKD are completely debilitating. And they're really driven by a dysregulation of mineral in the body. And I don't want to go through this whole graph because I'm sure many of you are aware of this, but that decrease in glomerular filtration drives an increase in phosphate load, which ultimately drives an increase in PTH. And this increase in PTH really precipitates cortical porosities forming, which lead to fracture risk. And so these are two mouse and rat models alongside a human model showing what these cortical porosities look like. And it doesn't take a biomedical engineer to recognize that putting holes in the cortex of your bone is not a good thing. And this is ultimately what's driving a large portion of the increase in fracture risk in these patients. So each of these diseases come to the table with unique skeletal deficiencies, which I've got a bunch of them listed here. It turns out that patients with comorbid diabetes and CKD have a 400% increase in fracture risk. And again, 50% or more die within 1 year following that fracture. The real kicker here is that very few animal models exist to study the comorbid disease state. Clinically speaking, patients with one or both are oftentimes excluded from clinical drug trials. So we really don't have, there is literally no treatment on the market right now to combat the skeletal deficiencies that are being driven by these disease states. And this is really what drove my lab to start looking at ways that we could develop combined disease models to study the impacts of disease and treatment in a controlled lab environment. I'm going to talk about one very quick study. This is the first model that we got off the ground, and it's actually the basis of my recently funded VA grant. So in this particular model, we induced diabetes using streptozotocin, which is a drug that ablates the beta cells in the pancreas. We induced chronic kidney disease using a diet that's laced with adenine, which causes crystallization to form in the kidneys, reducing kidney function. And then we also developed that metabolic bone disorder portion of the disease by allowing both diseases to manifest in age over time. And so What I want you to appreciate here, on the left is a picture of a kidney. This is a CT image. So this is mineral that's being shown on a CT scan. This kidney is packed full of crystals that have been formed by that adenine diet. The middle image is a heart. This is crystallization that's occurred within the heart itself. I don't have the aorta here to show it, but the aorta also shows vascular calcifications to go along with this really immense mineralization pattern in the heart. And then we're able to reproduce the cortical porosity, which again, from a skeletal perspective, is the clinical hallmark of chronic kidney disease. When we look at the disease state and we characterize how diabetes manifests and as kidney disease manifests, you can see here that we've got chronically elevated blood glucose in the animals that were treated with STZ, and markedly elevated HbA1c at the study's endpoint, which again is the clinical manifestation of glycated hemoglobin. It's the clinical measure that's used to longitudinally track the disease progression. From a kidney disease perspective, we have elevated blood urea nitrogen, which is a marker of kidney dysfunction. And you can see on the right that PTH, which is what we believe is driving cortical porosities, in the animals treated with adenine and no STZ, there's a much higher PTH. And although elevated still in the adenine-treated STZ animals, that hyperparathyroidism is blunted. Yet we still get the development of cortical porosity in all of these animals, along with cortical thinning, which you can see is what's crazy in the STZ adenine animals is that there's so little bone there that's left after the progression of the disease that even having that little bone, we still see the cortical porosities forming within the structure. Mechanically speaking, both disease states markedly decrease mechanical properties. And the hope here was that we would get significant interactions, which would tell us that the combined disease state was, much, much worse than either individual disease state. From a strictly statistical perspective, that didn't show up here. But when you look at statistical effect size, which is really a better measure of how big of a change is actually happening within your various groups, you can see that in most cases, the STZ adenine groups had effect sizes that were at least additive, if not more, than their mono disease counterpart. So we do think that we've developed a fairly robust model of combined chronic kidney disease and diabetes. In clinical settings, it's the diabetes that drives CKD, and that's not exactly the model that we have in the lab. So we're currently working on other models of diabetes that may in fact have kidney involvement. The most promising right now is this genetic KKAY animal, which is a chronically obese mouse that spontaneously develops type 2 diabetes. And after the time points that we've looked at right now, 16 to 18 weeks of age, are starting to show signs of diabetic nephropathy. It's mild at best, and we're hoping that over time that these will progress into a more robust disease state. So with that, I want to just take a step back and say we're studying a lot of different things. I was only able to touch on a very small portion of it, but I'm always happy to talk about the work that's going on in the lab. And so we've got time for questions now, and you can also feel free to contact me directly if you want to learn more. Thanking everybody that's been involved in these studies again. And again, this is how you can find more information about what we're doing.